Okay, we're going to look at how we can find the shortest distance between a point in 3D and a line. And there's actually 3 different ways to do this, so I'll show you all 3. But first I'm going to show you what I think is the quickest way, given the information we're given in this problem. And that is let's just do this in general first before we do it for this specific problem. But notice we're trying to find this distance d over here. And one thing I can pull out given any line is a point on the line. That's the p naught that's listed. And I can also point out a direction. So let's just pull out this direction vector and say that it's this vector v. Now let's just draw a little triangle and use some trig to figure out what it is we're trying to find. So let's call this vector from p naught to p. Just for shorthand, I'm just going to call it w. And we'll just label this theta. And so I want you to notice, just using some trig, what is sine of theta? So this is just on the side. Notice that sine of theta is going to be opposite over hypotenuse. So that's going to be d over the magnitude of w, which means this distance that we want is just the magnitude of w times sine theta. Okay, now I don't know what theta is right now, but I want you to think about what vector operations we've learned so far that involve sine theta, and hopefully what's coming to mind is the magnitude of the cross product. So recall, if I take the cross product between 2 vectors where the angle between them is theta, the magnitude of that cross product is the product of their magnitudes times sine theta of the angle between them, which means I can now solve for sine theta in terms of cross products and magnitudes. And then I can just come right back here and replace that in my equation. And so then notice this magnitude cancels with this magnitude, and I'm left with this for my total distance, or shortest distance between the point and the line. Okay, so now let's try it for this specific example and this specific point. Go ahead and put this on pause for a second and see if you can calculate it first. All right, so first let's pull out what these objects are in this picture based on this line equation. To find the direction, I'm just going to look at the coefficients of t in each of these terms. And so that means I have 2, -2, 1 for this direction. And then to find a point, I can choose any point on the line. I always think an easy point is just to let t be 0. And so in that case, this point would just be 0, 6, 3. But you could let t be anything. It doesn't matter what point we pick. Okay, so based on these 2 data points, my w is going to be, we already know p. P is given to us in the problem as 0, 1, 3. So that means w, which is p0p, is going to be the vector 0 minus 0 is just 0, 1 minus 6 is -5, 3 minus 3 is just 0. Okay, so now let's take the cross product with w and v. Okay, and when we do that, we should get -5, 0, 10. Distance is just going to be the magnitude of this vector, which is the square root of 125 in the numerator, divided by the magnitude of v here, which is just going to end up being square root of 9, which is 3. So I get square root of 125 over 3, which actually will simplify to 5 square root of 5 over 3. Okay, so that's usually the way I would try first, just because it's typically pretty quick. But there's a couple other options. So one other way we could think about this problem. And now a second way we could do this problem is actually using what we know about projections. So notice that if I take the projection of w onto v, it's going to give me this orange vector, which means that this vector right here, which the magnitude of which we want, is actually going to be the orthogonal projection. So what we're looking for is the magnitude of the orthogonal projection of w onto v. And we can get that by finding the regular projection and then subtracting that using just vector subtraction, subtracting that from w. So here's the other way to do this problem. And now I want you to try it. Put it on pause and see if you can find the answer this way. Okay, so just summarizing, when you do this, this orange vector is what you should get for your projection vector. And then when you subtract them, you'll end up with your orthogonal vector, and you take its magnitude, and we get back to the same answer that we had with option 1. Which leads us to our last option, which is actually just thinking, okay, I want this distance, and so really I can take the distance from my point 0, 1, 3 to any point on the line, and literally I'm just taking the difference then between the x components here, the y components here, and the z component here, and that's giving me this distance function that's now just a function of t. Then I can go back and say, well, I want to know when this distance is smallest, and this should be ringing a bell as a Calc 1 optimization problem. Find the minimum of this distance function. And so I can do that by taking the derivative, setting it equal to 0, and solving for t. But you may remember a nice shortcut in Calc 1. When you're minimizing distance, it turns out that the minimum distance will occur at the same location as the minimum distance squared. So we would often in Calc 1 just minimize d squared instead, so you didn't have to deal with the square root. So we'd make up a new function. Here I'm calling it f of t, which is just what was underneath the square root. And now I take its derivative, set it equal to 0, and that's going to give me a t value where the distance squared as well as the distance will be minimized. And so I can go ahead and plug that t value back into my distance equation, and that should give me the minimum distance as well. And just to clarify, instead of t here, I'm really plugging in 10/9 right here for t. I'm also replacing this with 10/9. And then when I simplify, I'll get to 5 square root of 5 over 3.